Everybody, this is Michele Veneri from Istituto Nazionale di Fisica Nucleare section of Naples, and I would like to thank the organizer for allowing me to present my work. Nevertheless, I'm not with you there in Patagonia. My talk today is going to be about enabling deep learning development and science for ALMA, which is a task that has been carried out within the Bayesian reconstruction within adaptive image notion, also known as BRAIN project, which is an ISO internal development study to investigate new methods for the imaging part of the ALMA data reduction pipeline. The BRAIN project is not carried out only by me, but by a large group of researchers scattered between ISO, UNINA, University of Naples, and the National Institute of Radio Astronomy in Bologna. First of all, let's dive a bit into radio interferometry and understand what's this imaging problem. Now, radio interferometers are inverse imaging device. Basically, they record the correlations between the antennas and which are known as visibilities, and they are related through the Fourier transform to the distribution of the sky brightness. Now, interferometers do not observe at a single frequency, but usually they observe in a bandwidth in frequency, and thus their data product is not an image but a cube containing an image of the sky for each of the observed frequencies. Now, the imagery problem from radio astronomy comes from the fact that due to the incomplete sampling of these UV space of the visibilities, in order to recover the true sky model from the observed sky, you need to deconvolve this observed sky by the dirty beam and primary beam, which are two complex spreading patterns that one comes from the gain pattern of the antennas and the other from these incomplete Fourier sampling. Of course, also you have the presence of several noise components, the atmosphere and the readout noise and so forth and so on. Now, this problem is classically attacked through iterative methods that try to separate, going back and forth between the UV plane and the image plane, the underlying signal from the PSF of the instrument. This is an iterative process which is quite slow, and thus there is a huge interest given the expected improvements that ALMA will receive in order to improve the velocity with which and also the quality with which this operation is carried out in production in ALMA. Now, if you want to try and attack this problem, of course, the first thing that you need to do is to actually retrieve ALMA data. And this is quite a slow process in reality, because in order to do so, you have to go on the ALMA archive, select the data that you want. Then for each 10 observation data cubes that you want to produce, you need to write a separate email to the ALMA help desk, which will respond to you after some times with the complex correlated visibilities that they have produced by running the pipeline on the data that you have selected. Once you get the links, you need to use CASA, which is a tool developed by Enero and ISO in order to transform these calibrated visibilities in the actual dirty cubes. Now, depending on your knowledge of radio interferometry and your hardware, this process takes around 1 to 4 hours for a single cube, which of course is a long time, and it means that you cannot apply together the large amount of data that is needed to train deep learning model. Moreover, even if you have the patience to do it, there are several problems with this data. The first one is that you only get the dirty cubes. You have no information about the underlying sky, and thus you cannot train supervised methods. ALMA is an instrument capable of observing with a wide range of configurations and that observe a wide range of targets. And so you end up having only few sources and few observing condition per target of interest. So it's really hard to really sample completely the what we call the ALMA observational parameter space. Of course, you have only partial information of the detection within each of these cubes because they will depend on the fact that someone ran a source detection pipeline on them. You have no information about the noise properties because they are not recorded in the ALM archive. You assert only partial control on the CASA pipeline, so you really don't know which were all the pre-processing steps that were performed on the data itself. And which means basically that you cannot assess easily your model baselines in order to improve upon the state of the art. To sidestep all this problem, I created the Python simulator, which is called ALMA-SIM, that basically wants to help you gather all the data product that you need, organize them, and simulate sky models which are closely related to the real data as they can be given our knowledge about radio interferometry and the information available in the archive. All of these is done while hiding the complexity of of the process to the user itself through a graphical user interface, which is the one that you should be seeing right now on screen. The idea of ALMA-SIM is that simulating radio interferometry sources is a three-step process, which starts by querying the ALMA tap interfaces for metadata in data itself. The software allows the user to create through the graphical user interface quite complex queries that will select the data based on the properties that you deem are important, like field of view, band, integration time, type of objects, and so forth and so on. When this is done, we employ a library of 120 lines spread between the submillimeter and the radio domain, a set of spectral energy distribution to simulate the continuum emission of these sources. And basically, we combine these two, assuming an underlying infrared luminosity of the radio sources to produce the expected line fluxes. We created this line fluxes for a subset of ALMA observation studied by Kirkpatrick et al. We found that the distribution of the simulated sources line fluxes was very similar to the real distribution observed with the redshift of those sources. Once it is done, we have let's say, the spectral part of our observation done, but then we need to take account of the morphology of the sources. And for that, we basically have a database of sky models that we create on the fly, which go from very simple point and Gaussian sources to very complex extended galaxies or molecular clouds. Once basically the sky model is in place and it's in the cube, it represents basically the perfect observation of this object made by an interferometer, which is completely sampling the UV space. And basically then we simulate the radio interferometric observation of it. We have a complete radio interferometric simulation that employs Dask to basically generate the dirty cubes and the also dirty visibilities in parallel through Dask. When we basically took a sample of around 40 QSOs from the ALM archive and extract their observational parameters, of course, and their scientific characteristics, and we simulate their counterparts with ALMA-SIM, we were able to actually measure their observational and source properties, and they were completely matching the ones that we were able to produce with ALMA-SIM, which means that basically with ALMA-SIM, given a type of targets, we can recreate simulated sources which are statistically similar from a data point of view to the real ones. And thus, we deem that they are a good candidate to train deep learning models. What we did after that is that we basically took the focus, which is a meta learner that I've created. A meta learner, it's basically a deep learning model, a PyTorch class in reality, that can rearrange itself to emulate any other deep learning model. there is a library reality of dense net, rest nets, UNet, transformers, and so forth and so on. And basically, if you characterize each of these networks by a set of what we call topological parameters, like for example, the number of layers, the activation function, you can explore this parameter space. In order to explore this parameter space, we use a technique which is called Bayesian parameter search. Basically, the idea is that you need a surrogate model, so a probability model for your deep learning model itself, that will give you at a given point of this parameter space the normal distribution of your prediction of the deep learning model performance on that point. And then you need an acquisition function. So something that will tell you where you want to sample in the parameter space. Basically, by finding a balance between maximizing the uncertainty of your acquisition function or its mean, you can sample point where you will be quite sure there will be an improvement of your deep learning models. Once we took the simulated data and we trained the focus to solve the convolution problem for high redshift QSO, we found not only our reconstruction was 2 order of magnitudes better that you can obtain with T-clean, but also the velocity of which we could produce these cubes was around 200 times faster than that of T-clean, or 5,000 times if you take into account the cost of GPUs with respect to CPUs. So this is it. Thank you very much for the attention, and see you at Astroinformatics 2025, hopefully.